Hello. In this video we will discuss about the dynamic mechanical thermal analysis, but before we go there we will continue our discussion on dynamic mechanical analysis and solve one or two problems. So, here is a quick summary of what we discussed in previous video. We said for an strain input written in terms of the exponential function e power I omega t, where it captures both the cosine as well as the sinusoidal inputs, the output can be written in terms of E star, which is the complex modulus times the strain input, where again we said the complex modulus is sum of the storage modulus plus I times the loss modulus E double dash. Similarly, for a stress input, we showed the strain output is written in terms of the complex compliance, which again is written in terms of the storage compliance D dash and the loss compliance D double dash. Finally, we have also seen for a strain input written in terms of cos form, we have derived what is the stress response. When we showed the stress response, we said it composes of two terms. The first term is in phase with the input, because both are cos, the input and the output, and the in phase term is governed by this storage modulus E dash, but the second term is the out of phase, because it is written in terms of sine. We know that sine and cos are perpendicular to each other or out of phase, and this is governed by the loss modulus E double dash. We also showed with a pictorial how we can see the input, which is this cos term, that can be written as a summation of two responses, one in phase and the other out of phase. So, the blue one here is the in phase and the red one here is the out of phase component. Okay. But when we discussed in the previous video, we are yet to know how to find these E stars and D stars. So, which are the complex modulus and the complex compliance. So, now let us see how to find these. So, let us start with trying to find the compliance modulus. For this we will start with the standard form. Previously when we were discussing about the mechanical models for Kelvin, Maxwell, we were able to write the differential equations, and when we wrote, we said there is a standard form, meaning we have all the stress terms to one side of the equation and the strain terms to the other side, and we write in the increasing order of the derivative, starting with sigma, first derivative of stress, second derivative, and so on and so forth. So, this is the generalized differential equation for a viscoelastic problem, but now let us see if we consider a strain input, meaning epsilon of t, we said it can be written as epsilon naught times e power I omega t. For this we said the response stress can be written as E star times the strain input, which is again epsilon naught e power I omega t. Now, let us see what are the first derivatives of the strain and stress and the second derivatives. So, we see how do we substitute into the standard form. So, first let us see at the first derivative of the strain, which is simply epsilon naught is a constant and e power Ax can be written as the constant times so here we write it as I omega times e power I omega t. Similarly, for the stress, E star is not a function of time. Later we will see actually E star is only a function of the frequency omega, but since the derivative is with respect to time, we only have it time is there only in the exponential. So, it is again I omega times e power I omega t. Now let us see the second derivative. For strain, we can write it as epsilon naught times I omega square e power I omega t, and similarly second derivative of stress is okay. Now we see a pattern. Let us substitute these and see how we can write it in a more compact fashion. So first let us see, we should be able to write the standard form in terms of a summation. So once we do that, the left hand side is, let us say k is equal to 0 to n, let us say we have n terms for the stresses, then it should be, we should be able to write it as pk times d by dt power n, meaning the nth derivative for stress. And to the right hand side we will write it as one more summation going from 0 to m, where m is the number of terms we have in the for the strains. It will be qk times d by dt power k and strain. I need to fix this, here this is not n but k. K is the index we are looking at. Now let us substitute this stress and strain as well as the derivatives in the standard form. So then we should be able to write this as summation k is equal to 0 to n p of k. For the stresses we will write it as E star times epsilon naught times I omega power k times e power I omega t. To the right hand side it is almost the same, other than we will have these qk terms and we do not have these E star. So, it will be simply epsilon naught times I omega power k e power I omega t. So, now let us see which of these terms we can take out of the summation. E star we can take it, epsilon naught and e power I omega t. Only terms which will remain in the summation are the pk and I omega power k terms. So, then we should be able to write it as E star epsilon naught e power I omega t summation of pk I omega power k. To the right hand side the constants which will move out of the summation are epsilon naught e power I omega t, and in the summation we have these qk and I omega power k. So, we notice that this epsilon naught times e power I omega t is on both sides, which can be cancelled out. Now, this should reduce as E star equals summation k going from 0 to m qk I omega power k by summation k going from 0 to n pk I omega power k. So, this should be our final expression to find the complex modulus. We started with the strain input in terms of the exponential and wrote the stress output, and then we have seen what is the pattern we are getting for the derivatives. Once we substitute that in the standard form, we are able to come with this expression for the complex modulus. Now, for the complex compliance, we can follow the same procedure. The only difference will be here we will start with stress input. And then the strain response can be written in terms of d star this time, which is the complex compliance, times the stress input, which is sigma naught e power I omega t. Then we will follow again the same procedure, but let me directly write D star now, because we have seen the procedure in the previous slide and the procedure is almost the same. So, here D star can be written as summation of Pk I omega power n power k and summation of Qk I omega power k. So, this will be the expression we get for the complex compliance, and we have already seen the expression we have for the complex modulus, which we will notice is just a reciprocal to the complex compliance. So, in fact, we can write that D star is 1 by E star, or the same thing can be written as E star times D star equals 1. So, this is an important observation, because later we will see it allows us to go from the complex modulus to the complex compliance easily, because we know the expression relating both of them. So, now let us see how this approach can be applied to solve a simple problem. For that we will choose the Kelvin model. So, for a Kelvin model we will first find what is E star and then also show what is D star. Previously we showed for Kelvin model this is the differential equation. So, written in terms of a standard form, I can write this as P naught sigma equals Q naught epsilon plus Q1 epsilon dot, which gives me P naught equals 1, Q naught equals E and Q1 equals mu. So, once I know this, now it will be easy for me to find E star, because we know a standard expression for that, which is summations in terms of Qk first in the denominator we have Pk's. So, once I substitute these P's and Q's, it should be E plus mu times I omega by P naught is 1. So, this is an expression for the complex modulus, but looking at this now I should be able to write what are the storage and loss modulus, which is pretty straightforward, because we know E star is simply the storage modulus plus I times the loss modulus. So, from here I should be able to write E star equals E and the loss modulus is mu omega. Okay. So, now we are able to show the complex modulus, both storage and the loss modulus. Now, let us see how we can calculate the D star, which is the complex compliance. So, D star is simply 1 by E star, which is here as E plus mu times I omega. So, now I should be able to separate the real and imaginary terms. To help me do that, I can multiply and divide by E minus I mu omega. So, the numerator is the same, but the denominator is E square plus mu square omega square. So, from this I should be able to separate the real and imaginary parts, which are the storage compliance now is E by E square plus mu square omega square, and the storage compliance loss compliance is minus mu omega by E square plus mu square omega square. So, what we have shown here is, once we know the differential equation for a particular material, the way the differential equation to define the viscoelastic response. From that we should be able to find what is E star and D star, or the complex modulus and the complex compliance. Now let us see, once we plot it, how they look like. So mind you, here in this slide we have shown that both the E star and D star, what are they are functions of omega, meaning E star is a function of omega as well as D star is a function of omega. So once we go to the next slide, that is what we will see, how these values change with frequency. So once we talk about E star, without saying it goes both for the storage and loss modulus also, these are all functions of the frequency. Similarly, the storage and loss compliance are also functions of frequency. Okay. So here we will show this response for the Maxwell model. So for this expression, for this example we have chosen the modulus as 900 pascals and the relaxation time as 15 seconds. So the blue curve here is the storage modulus and the red curve here is the loss modulus. We also show this another curve, the tan delta. I hope you remember the tan delta we have defined as ratio of loss modulus by storage modulus. Okay. So once let us focus on the storage modulus, we see at very low frequencies it is almost constant. The same is true at high frequencies, the value is constant. But intermediate frequencies, let us say between 10 power minus 2 and close to 10 power 0, that is where the modulus values increase significantly. So let us see how is it related, because if we notice this relaxation time is 15 seconds, since we are focusing on the frequency, that value should be somewhere here. So the value where we have seen the peak in the loss modulus curve, this corresponds to 1 by 15. So which is between 10 power minus 1 is 0.1 and 0.01. Okay. So what we are able to see is how these storage modulus and the loss modulus vary with the frequency. For the storage modulus we said it is constant at both low and high frequencies, but at intermediate frequencies there is this significant increase. But when we come to the loss modulus, if you recall, loss modulus we also said is proportional to the dissipation in the material. So energy dissipated during this loading. So we see that the maximum energy dissipation happens about the relaxation time, which is given as 15 seconds or 1 by 15 if we write in terms of frequencies. So it is peaking at this 1 by 15, but again if you are looking at very low frequencies or very high frequencies, it is almost negligible. Okay. So now what we will do is, now that we have this plot and we know how we are able to get this plot, right. So basically once we know the differential equation for the Maxwell model, we should be able to find what is E star. Once I find E star, I should be able to come up with this plot. Okay. Now the same results I will plot it in a different fashion. So the only difference between the plots on the left and right is the x axis. Earlier it is a function of the frequency omega. Now it is 1 by frequency, meaning we are plotting it for 1 by omega. What does 1 by omega signify? let us see with an example. If we are talking about low frequency, meaning let us say this is a specimen and we are doing this axial test in a cyclic fashion. If I am saying that the frequency is small, which means the loading is happening very slowly. But in contrast, if I say the loading frequency is high, means the strain rates it can see or the stress rates it will see are higher, which means this also indicates time in this expression. So, what we are saying is, so for example, 10 power minus 2 corresponds to 0.01, but 1 by omega value for here will be 100. Similarly, at 10 square, if we know of course this is 100, but 1 by omega value here is 0.01. So, at this point where 1 by omega is 10 power minus 2, the time scale is high, meaning it is a relatively faster test. But when we are looking at 1 by omega is 100 and meaning 1 by omega is 0.1, it is a low frequency test. It is just a flip compared to the left and right, the x axis is flipped up. The reason why we plot it in this fashion is actually we are used to, if you recall, previously we were talking about how the modulus changes with temperature. That is where we have defined these 5 regimes, if you recall, the glass regime, viscoelastic regime, the rubbery as well as the viscous and the degradation. So, we are used to seeing the modulus in this fashion, right. So, it starts with a very high value like the values seen here, and then at the relaxation times the modulus drops down, that is what we are seeing in this region, and finally these modulus reach to a low value here. That is the reason why in addition to plotting with frequency, people also plot it as 1 by frequency. So, this should summarize our discussion about the dynamic mechanical analysis, where we said once we do a frequency sweep, meaning going from a low frequency to a high frequency, we see at each frequency how the modulus varies. But there is another way to do this experiment, meaning instead of changing the frequency, we will keep it constant. But what we do is we do a sweep of temperature, meaning we will start with a very low temperature and gradually heat it up. So, meaning this cyclic test is happening at a constant frequency, we are not changing the frequency, but the temperature changes. Now, let us see how the response looks like. So, here we see the modulus variations. So, here is the storage modulus, loss modulus and tan delta, how they vary with temperature. So, this kind of analysis is called the dynamic mechanical thermal analysis. We introduced this term thermal because now we are bringing in the temperature contribution as well. So, now let us try and see how this is similar to what we have seen earlier. Earlier the x axis was frequency. So, the frequency was going from a low value to a high value, and we were watching or we are looking for how the modulus values vary with frequency. So, now what we are saying is we will keep the frequency constant, but varying the temperature we are looking at how these modulus values vary, which is now the DMTA, standing for dynamic mechanical thermal analysis. Okay, now let us focus on one at a time. So, let us focus on the storage modulus, which is shown by this green plot. So, at low temperatures we expect the material to be in a glassy state where the modulus is high. So, this matches with our earlier intuition. But then when the temperature reaches the glass transition temperature, that is when we notice that it moves from the glassy phase to the viscoelastic phase, where there is a sharp drop in modulus. So, that is what we are looking at. So, these storage modulus values are decreasing, but once we heat it up beyond the glass transition temperature, that is when it reaches more or less constant. Here there might be a slight increase, but it is not significant. Okay. Next let us move into the, let us focus on the loss modulus. Loss modulus shown with red, this is the loss modulus. So, initially at low temperatures these values are more or less constant, and then we see some peak happening at the glass transition temperature somewhere here. But after the glass transition temperature the loss modulus value is significantly reduced. Okay. So, we have seen the storage modulus and we have seen the loss modulus. Now, let us focus on the tan delta. Tan delta, which is simply the ratio of the loss modulus by storage modulus, which is shown here in blue. So, we see that at low temperatures as well as at high temperatures it has a very negligible value. It has some significant numbers at close to the glass transition temperature. So, here we have seen it is increasing and then decreasing. Okay. Now, we have seen the trends of the storage and loss modulus as well as tan delta, but now let us come to the interesting observation. The reason why people use this DMTA is also to know what is the glass transition temperature Tg. Okay. So, there are many ways to determine Tg, but the most common method is to follow the peak of tan delta curve. So, what is the peak of tan delta? We have seen for this, this is a plot for an epoxy from this literature. We can notice that the glass transition temperature here is 122.8 degrees centigrade. Okay. But in literature there are instances where people have reported the glass transition temperature using the storage modulus, which will be about 90 degrees, and there are instances where people have noted this glass transition temperature based on the loss modulus, which is close to 110. As we notice, depending on your definition, whether you are looking to find the glass transition temperature based on tan delta, you have it at 122. If it is based on the storage modulus 90 and based on the loss modulus it is 110. The variations are huge. So, it is very important to report this glass transition temperature also with the method by which you have reporting it. So, when I say the glass transition of this epoxy is 122, I should also emphasize that this is based on the peak of tan delta. Without that there could be misleading conclusions, because by other definitions the differences are as much as 10 or even 20. Okay. But the take home point is we use this dynamic mechanical thermal analysis primarily to find out the glass transition temperature, because this is a very quick way to find this temperature. We have already discussed and see why we want to know this glass transition temperature, because this is an important factor which says how a material behaves at the glass transition temperature as well as below and after that. It also helps to choose a particular polymer for a particular application. So, let us say the kind of we are operating at sub-0 degrees centigrade. We need to ensure that the material is hard at those temperatures. How do we ensure? Then we need to ensure that the glass transition temperature is much beyond your operating temperatures, meaning that it should be much above your operating temperatures. So, finally, let us summarize what we have discussed in this video. We started with discussing about the dynamic mechanical analysis, but then we showed you the expressions or derivations of for E star, the complex modulus as well as the complex compliance. Later, taking a Kelvin model, we are able to derive these E star and the D star. Finally, we have shown it for a using a plot how these values vary as a function of frequency. So, we may by doing a frequency sweep going from low frequency to high frequency, we have seen how the modulus values and the tan delta values vary. Finally, we also discussed about this dynamic mechanical thermal analysis, where we said we keep the frequency constant, frequency is constant, and we vary time. So, here we showed that about the glass transition temperature, we will see a peak in the tan delta curve, which we use to report the Tg value or the glass transition temperature values. So, with this we will conclude this video. In the next class, we will look at another interesting topic called the time temperature superposition principle.